This is Unit 3, Block 1, Example 5. We've been asked to find local extrema of this given function, so we need to find local max and local min of this f of x function. First, we need to find the derivative. Notice we do have a function f which is a product of two elementary functions. So you may think of the first function as little f, 25x. And you may think of the second function as little g, e to the negative 0.04x. We're going to need to use the product rule to find the derivative overall. So that's f prime g plus fg prime. F, in this case, is the 25x. G is e to the negative 0.04x. So little f prime is just 25, and little g prime is e to the negative 0.04x times the derivative of that inner function, so times negative 0.04. Putting it all together with the product rule, f prime g plus f g prime. I'm going to clean that up a little bit, so I don't need all these parentheses on that first term. It's just 25e to the negative 0.04x. And over here, 25x e to the negative 0.04x minus 0.04. I'm going to write the minus 0.04 out front times the 25x times the e to the negative 0.04x. All right, we found the derivative. Now we need to identify critical points of f of x. There are no places where f prime is undefined. You can plug in any x value to this f prime function and you will get a real valued answer out. You won't have any problems like dividing by 0 or square roots of negatives or anything like that. So you can plug in any x value. So now we can focus our attention on trying to find when f prime of x is equal to 0. So it is okay for you guys to use Excel Solver if you need to solve this kind of equation in this class. But in case you're interested in solving it by hand, I will show you that it's actually, it looks maybe terrible, but it's not so bad. You can factor this out and solve it pretty easily. All right, to solve this equation by hand, I'm going to go ahead and factor it. Notice what we really have is two terms. We have this first term minus this second term. When you have terms added or subtracted together, you can factor out greatest common factors between them. So I first observe that both terms have a common factor of 25. I'm going to factor that 25 out front. I also observe, so I've now factored out the 25. I've also observed that both terms have a factor of e to the negative 0.04x. So I'm also going to factor that out front. So I've factored out both the 25 and the e to the negative 0.04x. Then we write our parentheses because we're factoring that out front. The first term I've factored out everything, so all that leaves in the first term is 1. In the second term, I've factored out the 25 and the e to the negative 0.04x, so that leaves the minus 0.04 times x. So now I have written our f prime function in factored form. Now we can go ahead and solve this using the zero product property. Remember, if you have one factor times another factor and the equals 0, that means either the first factor equals 0 or the second factor equals 0 or both equal 0. So to find the solutions to the equation, we can just set each factor to 0 and solve. So I take this first factor, 25e to the negative 0.04x, and set it equal to 0. And I take this other factor, 1 minus 0.04x, and set that equal to 0. And now I just need to solve both of these equations. The first equation here on the left, there are no solutions to this equation. I know that because on the left, we have an exponential decreasing function. That is an exponential function. It looks like this if you graph it. And exponential functions never equal 0. That thing will never hit the x-axis. It never equals 0. So solutions to f prime of x equals 0 do not come from this factor. We now can focus our attention on the equation on the right. 1 minus 0.04x equals 0. I can add 0.04x on both sides. and then I'll divide both sides by 0.04, and 1 divided by 0.04 is 25. That's the only solution to the equation. There's only one critical point, one place where f of x is flat for an instant. That occurs at x equals 25. So there's one critical point, one place where f is flat. We need to now test to see if f of x actually has a max or a min or neither at x equals 25. At this point, I'm going to go ahead and open up Excel. In Excel, I have it all written out for us already. Let's just explore this a little bit. So I have put in x values, the f of x, and the f prime function. We see here at x is 25, the derivative is 0, as we said. And I make a conclusion. At x is 25, f prime of x is 0, so f is flat. We notice on the left side of that critical point, the derivative values are positive. Therefore, on the interval from negative infinity to 25, we see f prime is positive. Therefore, f is increasing. On the right side of that critical point, the derivative values are negative. So we can say on the interval from 25 to infinity, f prime is negative, so f is decreasing. And now we can make that conclusion because f prime is positive on the left, f prime is negative on the right. We can now conclude that f of x has a local max at x equals 25. We see that the function f increases, then flattens, then decreases. So definitely there is a maximum at x equals 25. Since it's in Excel, we can easily go ahead and make a little quick graph of this f function and see that that is in fact the case. And so we see at x is 25, there is a peak, and that is a local maximum.